Okay, good afternoon, everyone. So I'm quite excited to be here to present some of our recent work on using large language models to improve software quality. And I guess we can start. Yeah. Okay, so as we know that software nowadays is everywhere, which is great because they can make our life much easier, right? But unfortunately, sometimes bugs are also everywhere. So they can delay our trip, crash our cars, or even crash our airlines, right? So according to Tristantis, for example, like software bugs can cost us over $1 trillion every year and affect billions of people, right? So how do we eliminate software bugs? How do we improve software quality? And to do that, so let's take a look at a simplified software development cycle. So in this simplified development cycle, so developers need to first generate the code, right? And because we are human beings, when we write the code, we also generate a lot of bugs. And because of that, developers need to spend a lot of time to detect those bugs, to fix those bugs, and this process gets repeated again and again during software build cycles. And for large companies like Google, Facebook, Microsoft, they can have hundreds of thousands of builds every day. And developers need to waste tremendous time dealing with all those tasks, right? And fortunately, so there has been a long line of research to automate those tasks for the developers, right? So we have techniques on program synthesis to directly generate programs from scratch. We have testing techniques to help developers to find bugs. We have repair techniques to help developers to fix bugs, right? And of course, this is not the topic of this lecture, so I'm going to instead ask a question. So how would the recent large language models impact all such tasks, right? How would large language models affect the previous research we have done in the past decades? So that will be the main topic of this lecture. And before going to the details, I'd like to introduce a little bit about the background about large language models. What are they, right? So basically, large language models, so they are just models that assign probabilities for token sequences. And everything is just about probability computation, right? And they are basically built on the transformer architecture, so with the attention mechanism, right? So for example, if I want to produce this line of code using large language models, so everything will be about probability. So for example, the probability for producing this statement will be the probability for producing every token based on the earlier ones, right? So, and of course, when we produce every token based on the earlier ones, we pay different attention to the earlier tokens. For example, when we produce the last token, so we pay more attention to verbal. The reason is that we are trying to sum up verbal and one, right? So there's some subtle type relations among the two. So the large language models, they are able to capture those subtle relations by using the attention mechanism. But now you may argue with me, okay, this kind of idea using some sort of probabilistic analysis to model the language has been there for over 7 decades. Even the Ngram model had some similar insight. So what's special about those large language models? So, okay, what makes them large? So basically, they are trained on using huge number of parameters. So for example, here I have a trend of the recent representative models. You can see that it has been reported that actually the recent GPT-4 model might have over 1 trillion parameters. And with those huge number of parameters, the model can learn store a lot of knowledge, a lot of information in the model, and to perform complicated reasoning and planning tasks. And they are also trained on large amounts of unsupervised data for pre-training. For example, they're trained on Wikipedia, like code from GitHub, or discussions from online forums. Those trillions of text tokens provide a lot of resources, a lot of knowledge bases for the large language models. Okay? And they have shown impressive performance in many of the NLP, natural language processing, like understanding and generation tasks, and also on some simple coding tasks, right? And in this talk, we are mainly focused on this question. So how do those powerful large language models perform in improving software quality in practice? How do they perform in realistic settings in dealing with real-world systems? So that's the basic topic of this class. I'm going to cover basically all these three tasks we have talked in the past. Now we're going to revisit them using large language models. So I'm going to introduce some of our recent work in each of the tasks. Okay, for testing, repair, and synthesis. So we'll start with testing. So, okay, so let's start with testing. So the particular problem we're looking into testing is called fuzzing or fuzz testing. So some people may have heard about that, but even if you haven't heard about that, it's a pretty simple concept. So the basic idea is that, so we want to automatically generate inputs or tests for a system so that we can discover potential bugs and vulnerabilities. And they are extremely easy to implement. So for example, this red line, it is a practical fuzzer. So what it does is that our Unix style system, we try to generate random strings and pass that into your system and try to crash your system. So you can literally implement one fuzzer in one line. And for the execution for every generated test inputs, you can basically monitor the test execution result, right? So if there are crashes, if there are errors, you can find potential bugs or vulnerabilities. So the idea is extremely simple, the core idea, but has huge impact in practice. There is a wide range of applications of fuzzing on real-world applications. I'll just give you one example. So this particular one example is called OSS Fuzz. This is a fuzzing project initiated by Google. So for already 6 years, and in the past 6 years, OSS Fuzz, this single project, has helped us to identify and fix over 8,000 vulnerabilities and over 28,000 bugs across over 800 projects. Okay, and those include a lot of influential projects like LLM, like Firefox, Maven, Hadoop, and more. Okay, so and of course there are many other projects trying to apply fuzzing to other domains to find critical issues in other systems, right? And the particular domain we are targeting first is called deep learning library fuzzing. So you may be asking, oh, why do you want to work on fuzzing deep learning libraries, right? What's special about that? So deep learning libraries like TensorFlow or PyTorch, they serve as the foundational building block for all the deep learning pipelines, right? So imagine the current extremely popular large language models, all the safety critical autonomous driving systems, in the end, they are all built with some sort of deep learning libraries. So you can imagine, if there are any bugs in those deep learning libraries, they can affect all those critical downstream applications. So this is a very important piece of software. That's why we started with this problem on fuzzing these deep learning libraries. And remember that the basic idea of fuzzing is to just generate random inputs for the system you want to test against, right? So then the problem is, what are the inputs for deep learning libraries, right? So and the actual answer is that you can generate arbitrary small deep learning programs invoking the APIs from the libraries, right? In this way, let's provide an interface to interact with the system, to test the system, right? So one example I'll give you is like this one. This small piece of code is going to interact with PyTorch and invoke certain PyTorch APIs and execute the PyTorch behaviors, right? And at a first glance, this sounds something very easy to generate, right? Some very simple piece of code. If we can generate this automatically, generate thousands of them, millions of them, we can potentially detect a lot of bugs in PyTorch or TensorFlow. But in fact, this turned out to be an extremely challenging problem. The first issue is that these deep learning libraries, they basically take input, take Python programs as input, right? So basically, Python is a general purpose language and it's dynamically typed. So generating valid Python programs is already challenging. And on top of that, those deep learning programs, they are playing with tensors. So there are a lot of tensor constraints involved in the small program. Even for this very simple Ford API, there is this super complicated constraints to ensure that the input shape for the shape for the input tensor, the shape for the output tensor, and also the other arguments, they must satisfy these complicated constraints in order to make this piece of code executable. Okay, so to summarize, this is an extremely challenging problem. So we need to deal with Python syntax, semantics, complex tensor computation constraints, the other implicit, explicit API constraints as well. Okay, so then how do we solve the problem, right? So the first idea came to my mind is that, okay, why not just start with traditional fuzzing techniques? Okay, so let's see, what are the traditional fuzzing techniques? So traditional fuzzing techniques can be typically categorized into two main categories. The first one is generation-based fuzzing. What it does is that basically generate input programs based on predefined language structure or grammar, for example, context-free grammar for Python. So then you can generate Python programs from scratch, right? And the other way is that instead of generating programs from scratch, you can use mutation-based approach, which just takes some existing programs as input and try to apply small changes on the program to generate even more diverse programs for fuzzing. So this is a mutation-based approach. So, but they are both quite effective in a lot of domains, But it seems to be like it turned out that they are kind of attempting to apply them to the like deep learning library fuzzing domain. So one reason is that, for example, for the generation-based approach, they require high manual effort to ensure the validity of the created programs, right? So for example, C-Smith, which is extremely popular like compiler fuzzer for C. And it has been proposed for 12 years, and in the past decade, developers have over 40,000 lines of code to implement this single fuzzer for C compilers. And even though, like that, this very, very complicated fuzzer can still only cover a very limited subset of C grammar. Okay? And the mutation-based approaches, they also have high qualities, require high quality Cs and high quality mutation patterns. They also need to involve a lot of manual effort to ensure the validity of the created programs. So it turns out that those traditional techniques can really hardly perform well even for generating valid Python programs, not to mention the deep learning programs, which are more complicated because deep learning programs also manipulate a lot of tensors, so they have additional tensor constraints on top of the Python programs. So it's an extremely challenging problem. So in order to solve this problem, so we came up with a totally different solution by directly using large language models for fuzzing. And our basic insight is that those large language models, they are pre-trained on trillions of open source code tokens, and they can auto-regressively generate human-like code. Right? So, for example, this is why traditional fuzzing techniques do not work for deep learning library fuzzing, because we need to handle a lot of constraints, right? The Python syntax semantics constraints, the tensor shape constraints, other API constraints. For the traditional techniques, you really need to explicitly model all of those constraints and then solve the constraints. That turns out to be extremely challenging. And so large language models provide another way. So in the area of large language models, maybe we don't need those explicit constraints. All we need to do is just to leverage some models that are pre-trained on a massive corpora about those deep learning programs. So they learn how to generate legit deep learning programs intrinsically. So for example, there can be over 400,000 TensorFlow PyTorch projects on GitHub, right? So any large language models trained on GitHub, they can implicitly learn to generate legit or valid programs like Python, TensorFlow programs or PyTorch programs. So that's the basic insight. So we will throw away any explicit modeling or constraint solving. We just let the model to learn. Okay? And that's the basic idea. So we directly use large language models to generate valid and diverse programs for fuzzing deep learning libraries. And because we are using large language models, so they are pre-trained on hundreds of different languages, right? So that basic idea can be directly applied to fuzz systems in any other languages as well. So it's a pretty generalized, generalizable approach. Okay? And this is the overall design. So basically, we have the generative. We leverage both generative large language models and infilling models. So the generative ones, they learn to auto-regressively predict the next token given the left-only context, right? And for example, if you have input equals torch dot, and then the decoder-only model will be able to complete a next token for you. This is very typical, right? And the other style of model is called infilling models. And what they can do is that they can actually leverage the bi-directional context rather than just left-only context. So for example, if I have this span, which is a placeholder here, right? And I can leverage large language models to learn from both the suffix and prefix to infill the most natural code to replace the placeholder to generate the solution. Okay? And both types of large language models, they learn how to generate human-like programs from trillions of code tokens. So based on that, we are going to use generative large language models like Codex for generation-based fuzzing. And we are going to use infilling models to mutate existing programs for mutation-based fuzzing. So that's the overall design. And this is a big picture about the tandem fuzz approach. So, the basic approach includes 3 steps. The first one is seed program generation. So we just use some generative models to generate seed programs like Codex. We can use some prompt engineering to generate valid deep learning programs, right? And then we dive into this evolutionary fuzzing loop, and we further use infilling models to further change the programs we generated earlier, right? So we can generate more and more diverse programs. Of course, we have some finish function to only keep the valid ones, like effective ones, so we can have more and more like programs for fuzzing deep learning libraries. So in the end, there's the oracle problem, right? So we did not use like language models for the oracle generation. Instead, we use traditional oracle, like differential testing oracle. Basically, for the generated code, like deep learning programs, we can execute them on both the CPU and GPU end and check for any inconsistencies, of course, right? And we can also check any crashes triggered by the inputs to find bugs. Okay. Next, I'm going to talk a little bit about the two main steps: initial seed generation and imitation. Okay. So for initial seed generation, the insight is that generative models, they can directly generate high-quality seed deep learning programs. For example, all this generative loss function for the generative models tells us that, okay, the models are trained to simulate how developers like write programs from left to right, token by token, right? And in this way, we can literally like prompt the models to generate programs first from scratch, right? So we use some step-by-step prompting for seed program generation. We use Codex as a generation engine. And of course, the idea is generalizable to other models as well. So this is one example we had. So we split the task into three like subtasks. For example, first you need to import the library, right? Second, you need to create some interesting data. And third, you need to call some API to perform some interesting manipulations, right? And after providing this kind of prompt to Codex, and Codex was able to complete some fairly legit and promising solutions like these ones. I was completely blown away when my students showed me like first time Codex was able to generate something like this 2 years ago. So it's kind of amazing tools. And for the evolutionary fuzzing part, so we use infilling models to directly fill in the code in the middle, given the pre and post context, to change the existing like programs we generated for fuzzing. So all this loss function tells us is that the models are trained to learn how to infill the most natural code in the middle of the bidirectional context. And we can leverage that insight for like a mutation generation, right? For example, we use a template-based masking, so we can create a lot of like template-based masks, and then we can use infilling models to infill those masks and to provide more programs for fuzzing. We use encoder as the engine. So I can give you an example. For example, if we generate like some seed input program like these ones, right? We can randomly mask out arbitrary locations within these seed programs. So then we can generate arbitrary new programs on top of this. So we can mask out, say, the argument values, we can mask out the suffix, mask out the prefix, or even mask out the API itself. And the large language models, they will be able to learn to infill the most natural completion using the bidirectional context to generate valid programs for more effective fuzzing. So that's the basic idea. And we have been evaluating that on real-world systems, like real-world deep learning libraries, like PyTorch and TensorFlow. And we have found over 60 bugs, and 55 of them have been confirmed as real-world bugs, and only 9 of them can be found by the existing fuzzers for deep learning library like domain. Okay? And here are 2 example bugs we found. One is a high-priority bugs for PyTorch, and the other one is a security vulnerability bug for TensorFlow. So the first one is like on the CPU side, you see that the CPU side counts all the not numbers, while the GPU side does not count that. So clearly inconsistency, meaning something wrong on the CPU side, right? And on the other one is that, so this TensorFlow bug is an out-of-bound read. Basically, they fetch some value from some other locations of the memory so that you have an inconsistent result among the two. So that's a kind of a brief overview about the results. And to summarize this approach, so this is the first large language model-based approach for fuzzing deep learning libraries and beyond. And we've been using both generative and infilling models for generation and imitation, right? And we achieve high coverage. We found a lot of interesting bugs, and it also has some interesting implications for fuzzing and testing in general. So this work demonstrated for the first time that large language models, they can basically automatically perform both generation and imitation-based fuzzing. People have studied for over a decade, right? For over decades, yes. And they can be fully automated. And they can target some domains that are pretty challenging for traditional techniques. And they can be easily generalized to other domains, including like other compilers, deep database systems, smart contracts, quantum systems, right? So I know that one question now for me is that, okay, you show that it's possible, but why don't you show me some result on that, right? So that's exactly the next work I'm going to briefly show. So actually we try to adopt this idea to fuzz systems from entirely different domains. Okay? And please also feel free to check out the paper for more details if you're interested in the technical details. Okay? So the next work I'm going to introduce is to extend the basic idea of tiling fuzz and use that to fuzz systems from completely different domains. For example, like the constraint solvers like Z3, CVC5, like C compilers, LVM, GCC, like Go toolchain, even Qiskit. This is Qiskit, the quantum computing systems. And you can see that for all the different systems, we need to provide different prompts in order to allow the system to generate, allow the models to generate like valid and diverse inputs to fuzz those systems, right? Of course, for every new domain, we can manually like do some prompt engineering, and we can do that, and it's not a hard job, right? But the goal for this work is to use auto-prompting to fully automate even the prompt engineering part for fuzzing different systems. So this work, which is called Fuzz for All, so we can take user input in any form or format, like for example, documentation, example code, specification. So given all those different sources of information, we use a powerful distillation model like GPT-4. So we ask the model to come up with candidate prompts. And then we evaluate all those candidate prompts by the dynamic feedback information. Okay? And so we can select the best prompt for every domain. And then we will jump into the actual fuzzing loop, basically using generation and mutation-based fuzzing for every domain. So the core idea is to use auto-prompting to automatically create the best prompt for different domains. And it has worked surprisingly well, although the idea is extremely simple. So we have been used that to test systems from a lot of different domains, as I mentioned, even including the quantum computing system. And we have compared our technique against a bunch of different fuzzing techniques from the specific domains. People have spent years or decades to engineer those tools. And that also includes some tools was recently published. And surprisingly, we found that such a universal fuzzer was able to beat all those domain-specific fuzzers in terms of line coverage. For example, we can outperform all these state-of-the-art baseline tools like by achieving over 36% high coverage. And we have already found over 80 new bugs, critical bugs for all the studied systems, including bugs for the quantum computing systems. And the number is keep increasing. Okay. And this work is published in XC24. So again, feel free to check out the paper for more details if you're interested in the technical details. And this is probably the end of the first topic on testing. I'm not sure if there are any quick questions you want to ask, I can answer. If not, I can just move on to the next topic. Any quick question?
Actually, I have a question.
Okay, go, sure.
It's interesting that it outperforms by 36.8. I was wondering how stable is it as compared to the previous techniques?
How stable is the technique, right?
Yeah.
So the question is that we are using large language models. So how stable is the technique in terms of performance? That's a very good question. That's exactly something we cannot control. Because in the end, it's all about probability, right? So what we're doing is that we are trying to run the fuzzers for a longer time so that it can saturate, so we can model the result more stable. Yeah. Good question, though. Okay, maybe I can move on. We can talk more after this talk, right? So the next topic will be about how do we leverage large language models to fix real-world systems. And this is the entire topic. It's called automatic program repair, or APR for short. And the goal is very simple: help developers to automatically fix their bugs, right? And this has been an extremely kind of extensively studied domain in the software engineering area. So people have proposed tons of techniques in the past decade since the proposal of the Jim Proc work, and with the recent focus on the neural machine translation-based techniques, those are the recent deep learning-based techniques for repair. And even a lot of industry companies, they have proposed a lot of repair techniques in this domain. Right. So, and our insight is that instead of performing repair edits using the idea of neural machine translation, right? So let's directly generate the correct code using large language models. So without any translation, okay? And I'm going to briefly show 3 of our work along this direction. And so we'll start with alpha repair, which is the first influence-style API general purpose repair technique. And this is a big picture about the earlier learning-based repair technique based on neural machine translation. So you can see that the basic goal is to translate the buggy code into the fixed code, right? Of course, some of the techniques also leverage some context information, right? But in the end, it's a translation task. If you want to train a model for translation task, like people need to really prepare an extensive and high quality bug fixing data sets. And that can be extremely hard to construct. Okay? And so our insight is totally different. Our basic idea is that we are going to directly use large language models pre-trained on trillions of code tokens, and we are going to leverage them to fix bugs based on the naturalness of the software. So what we are doing is that given any buggy code with a pre and post context, we can mask out the buggy code, replace that with some placeholders, right? And then we can use large language models to directly infer the most natural completion based on the context. So the basic insight is that the vast majority of the code in the world, they are the correct ones, right? So the inferred most natural completion should also be more correct than the earlier, buggy version. So that's the basic idea. And in this way, we were able to completely free learning-based APR from bug fixing datasets, right? So which are limited and extremely hard to collect. If you want to talk about details, I'm very happy to talk about that because myself, we have collected a lot of bug fixing dataset in the past. We have a lot of issues with that. And we have more natural representation of the context, right? So now instead of translating buggy code into the correct code, we are trying to leverage the naturalness of software. We try to directly recover the patch based on the bi-directional context. Right? So we have a very natural representation of the context, and we can capture also the subtle relations between the context and the patch. Right? And more importantly, the idea can be directly applied to any other languages as long as they are covered in the pre-training corpora of the large language models. Right? So how do we exploit the pre-training objective of large language models to perform this task? Of course, this work was done with CodeBird because we did this work over 2 years ago. And CodeBird was probably the best open source code model back at that time. It's a pretty small model. It's definitely not a large language model, but the idea applies. Okay, so let's take a look at CodeBird. So CodeBird was trained using masked language modeling or MLM, right? The basic idea is that during the pre-training phase, the arbitrary tokens in the pre-training corpora will be masked out. And then CodeBirds will be trained to recover those tokens, right? And you can observe that actually for influence sound APR, we have a very, very similar problem. The only difference is that we have only masked lines from the potential buggy lines. We only try to recover those potential buggy lines. That's the only difference, right? So they both aim to recover tokens masked out. So that's why we can actually directly leverage even small models as small as CodeBird for program repair. Okay? And this is the alpha repair basic workflow. Basically, given any buggy project, we first leverage some fault localization technique to identify the potential buggy lines and their context, and then we can mask out those buggy lines, right, to create the masks, right? And then we can basically generate all the candidate patches using CodeBird, and we can further rank those patches using CodeBird, and finally we can validate those patches against the test to find the final correct ones, right? So, and I'm going to introduce some main steps. For example, for input processing, what do we do with that, right? For input processing, what we do is that we take, for any buggy line, right, we take the context before, context after, and the buggy line. So we first take the prefix and suffix. We use that, definitely we will use that, right? And also we take the original buggy line, we transform that into some comments, because we believe some tokens from the original buggy lines can also be helpful to create the patch. And for the original buggy line location, we replace that with some masks token, with some placeholder. And all our goal is to recover that part to come up with a more correct patch, right? And how do we mask the potential buggy lines? Of course, one easy way, just completely mask out the complete line. This is probably okay for the recent models, but it was extremely challenging for CodeBird because of the limited generation capability of CodeBird. So because of that, we also have a lot of masking strategies. So we mask out a part of the line, like beginning of the line, end of the line, also mask out some function names, argument names. But I want to say that these are not necessary if you're using more powerful models. Even like CodeLlama will be sufficient to generate your legit patch without any specific masking strategies. Okay? And after you have a masked line, you can leverage large language models to come up with the potential patches. We just query the large language models to generate the tokens one by one, so we can have a bunch of different patches, right? And for those patches, we further re-rank them based on the probabilistic analysis in large language models to speed up the patch validation. And this is a summary of the alpha repair work. So basically, what we do is that we reformulate the repair problem as an infinite task or a closed task. So in this way, we don't need any bug fixing dataset at all. And we can have better context capture. We can have multilingual program repair by default, right? And we show that this can, large language models can outperform existing API techniques studied for over a decade. For example, on deepfake project 1.2, 2.0, we all have state-of-the-art result, like back that time when this was published. And this can be also easily extensible to different languages because we directly use language models without any bug fixing dataset even, right? And yeah, this is pretty much the idea about alpha repair. So, and alpha repair sounds quite interesting. So you can generate patches, right? So like you directly using language models. But there are some patches, they are extremely hard to generate because they can have rare tokens. They can have domain-specific tokens, right? So how do we, because those tokens may not even be available in the pre-training corpora of the large language models. How do we deal with that, right? So what we are going to do is that, for example, for the first one, this patch, this complete patch is to add a new function invocation, and this function can be really weird, right? And how do we come up with that? So actually the first idea came into my mind was the plastic surgery hypothesis by Prem and co-authors, right? The basic idea is very interesting. So the changes to a code base basically contain snippets that already exist in the code base itself. So which means if you want to generate some patch for the current project, the patch ingredients may have already been there in the project. And this is exactly true for this one as well. This function on the invocation, it must be defined somewhere in the current project, right? So our basically, okay, then maybe how do we leverage this plastic surgery hypothesis to help with better repair, but with the help of the new recent large language models, okay? So instead of manually encoding all those rules, we let large language models to learn all those information, okay? So in fact, there are basically two main ways. The first way is that this is a like project code base, right? So the first way is that we can definitely, compose some prompts for the model. So the model can have more information to generate some more interesting tokens specific to the product, right? So for example, we can use something like information retrieval, we can use static analysis, so we can prepare a lot of interesting tokens to guide the model in terms of to prompt the model to generate more interesting patches. The other way is that we can even fine-tune the model, retrain the model based on the current project to let the model to get familiar with the token in the current project, right? And this is exactly our idea. It's called Revisiting the Plastic Surgery Hypothesis in the area of large language models, which is published in AAC last year. So feel free to check out the paper for details. I'm not going to cover the details, yeah. And so this one is we completely rely on large language models to deal with the rare tokens, domain-specific tokens, right? The other way is that we can also combine large language models with the traditional solutions we have, right? For example, for this next patch, for this one, if you want to add this complicated token, so we can figure out that, okay, some part of the token, the models are good at generate that. Like the foundation models, large language models, they may be good at generate something in the beginning, for example, right? But once you have some context, the traditional completion engines, they may also do a good job in generating even some real tokens, domain-specific tokens in the current project, because they can perform a lot of syntactic semantic analysis of the project. Right. So that's exactly the next project, which is copiloting the copilots. So we try to copilot the large language models with traditional code completion engines. And this is published this year at FAC 23. We'll present that in California next month. Okay? And okay, so given the time, let me finish the last one. It will be very short. So the last topic will be on program synthesis. And so scary, right? So AI, a lot of models proposed every week, right? So for example, there is a very widely used data set called human evo. So for example, a lot of models claim to have a very high score, like 80%, 90% pass rate, for those problems. This is very scary, right? So can those language models really replace human beings? Are developers really fired, right? So is this really true? So that is exactly our motivation for this project. So because of that, so actually we look into the actual human evolved dataset because we work on testing in the past decade, right? So we want to see if the dataset is reliable or not. So we look into the human evolved dataset and we figure out that for every dataset there's a simple problem like this one, and for every every like a solution created by the models, they will be validated against a lot of test cases provided by the test, right? But are they sufficient? So for example, for this simple one, like ChatGPT can generate this solution, okay? And this solution pass all the tests in the existing human eval dataset. And the existing work will deem this as a correct generation, right? But is this really correct? I'm not sure if anyone can spot the issue with this. So in fact, so if you ever provide one more test, so this is the one generated by our new dataset, I'm going to introduce later, Human Eval Plus, okay? If you just add one more test, this solution will fail, okay? And the bug is here. You have a set operation, which will cause you to lose the sorted elements, okay? So, so such kind of weak tests in such extremely popular datasets can really largely affect the evaluation of all the recent like code models, including GPT-4, like GPT 3.5, and all the other open source ones, right? And our idea is very simple. Our idea is called Eval Plus. The idea is to simply combine ChatGPT itself with traditional techniques for generating new tests to better validate the solutions provided by the large language models. So we are going to use large language models to test the code provided by the large language models themselves. So that's the basic idea, okay? And I don't have time to go through the details, but I will have a one-page summary. So we have tested over 30 popular large language models, including both open source ones and commercial ones, and we have generated over 12,000 tests using ChatGPT and traditional solutions. We have run over 20 million test executions to test all those like recent models, and we observed a 15% average performance degradation for almost all the studied models. And we also have a leaderboard based on our evaluation results. So our dataset is called Human Eval Plus, so which is constructed by our Eval Plus approach, right? And we also have an Eval Plus leaderboard. So feel free to look into that if you're interested in the ranking of the recent models. And we rank all the models based on their original ranking in the original Human Eval and the new ranking using our more rigorous Human Eval Plus dataset, okay? And you can see that for the top 3 models, this is the old one I got. The new models is updating every day. So please check it out online, okay? So at the timestamp I look into this ranking, you can see that initially ChatGPT was within top 3, but then it drops to top 4. So there is some huge change between the ranking like of the two, like based on the 2 different datasets. And GPT-4, for example, originally has 88 pass rate, right? But now the score is only 76. So there's some very, very kind of substantial degradation on the more rigorous evaluation just because of the newly added tests we have for the dataset. Okay? And our dataset called Human Eval Plus have already got like over 400 stars on GitHub, has already been installed for almost 5,000 times on Python package index already. And also got some interesting tweets. For example, this is one I like the most. I don't know this person, frankly, right? But I really like the content. So there are too many ML papers focused on improving the performance on the benchmarks to achieve SOTA results, right? Finally, there's one explicitly focused on reducing the performance. I want to clarify that we don't intentionally want to, reduce the performance of the models, right? We just want to come up with a more rigorous evaluation to have more precise evaluation of the models. We believe that is very, very important for the domain to evolve, okay? And, okay, so of course, we talk about improving software quality in language models, right? And there'll be a lot of future work to do in this domain. We call it LLM for code, right? And for example, in the end, it must be some synergy between human beings and large language models. There are a lot of interesting problems, right? How do we leverage language models to boost and unify those tasks? How to train domestic models? I'm not going to cover the details because we have discussed a lot about that in the panels and everything in the event, right? And of course, the models, they are not perfect. We need to embrace them and also understand their limitations as well, right? And last thing I want to mention is that, so Prem, I, and 2 other colleagues, like Leading and Ling, we are launching the first international workshop on large language models for code, okay? So this will be co-located with ICSI 24. So if you are interested, if you have done some relevant work, please consider submitting to our workshop. The deadline is next month, okay? Okay, and this concludes my talk. I'll be very happy to answer any question you may have. Thank you so much.
All right, thank you. Any questions?
Okay, thank you for your talk. So a couple of questions. So first thing about fuzzing, especially fuzzing languages. One of the things that kind of limits the applicability of LLMs in fuzzing languages like C is undefined behavior.
Yes.
And it's why Sysmith, just tests part of
yes.
Clang or GCC. Can you comment on that, or how many undefined behavior did you have on your test cases?
Yeah, that's an excellent point. So for now, actually, we do not explicitly look into the problem. So what we are doing now is just to try to provide more relevant examples so that the model can learn to generate more legit programs, right? But I think in the near future, it will be very, very interesting for us to focus on the problem, see how we can leverage language, how we can avoid this issue using language models, right? There can be combination of like language models and traditional solutions, can be just some prompting, we don't know. But I think that's something very interesting to explore.
Yeah. So I think, the second question about, the part in program repair and the evaluation part, I was wondering whether you look into potential signal leakage, meaning that, because, CodeBird perhaps, has been trained on different versions or of the code, which may contain the patch already.
Very good point, very good point. That's an excellent point, yes. So actually we look into that issue. So basically of course, what we do is just something like information retrieval. Right? Let's see, okay, is there any something like with some n-gram embedding search, some ones that are extremely similar? If there are, we just try to exclude that from the patches to have some more fair comparison. But still, that can be limited because in the end, the embedding-based techniques, they cannot basically infer all the semantic equivalent ones, right? So I think in the long run, it will be very, very important to look into the data leakage issue for not only program repair, but for many of the other domains, like program synthesis as well. Very good point.
Okay.
Yeah.
All right, I guess we have time for one more question.
Thanks, really interesting work. I had a question about the fuzzing work. So the examples that you gave, even for Fuzz for All, they seem to be cases where the inputs were programs, which are going to be in domain for the large language models, exactly, which might kind of help it to do better at fuzzing. So if you were thinking kind of more broadly about OSS fuzz tasks, like if it was PDFs or something like that, how could you apply this kind of technique?
Yeah, that's an excellent point. So for now, what we are taking as input are basically structured input, like code or from different languages or like some structured files like XML files, HTML files. The models are good at those structured input, right? But for some of the domains, like for example, the AFL style fuzzing domains, so the input is just kind of like a bias, right? So how do we leverage language models to deal with those domains? I think that'd be something very interesting. Actually, our group, we are exploring some direction along that way. So we have some very interesting findings that even at the byte level, so there are some embedded information, and the models will be able to figure out something even at the bytecode level, and you can even decompile that into something very legit. So we can talk about that for more detail offline. Yes, very, very interesting question.
All right, thank you, Lingming, for your very interesting talk.